Okay, so let's start with the application in exercise 5.9. I'm gonna try to give you a complete solution. So I will try to show you all the details along the way to the full solution. So we have a single input production technology. This is a production function which is assumed to be continuously differentiable, strictly increasing, strictly concave, and the usual in other conditions hold. So at zero capital input, output is zero. If k goes to zero, we have a huge first derivative, and if k goes to infinity, the function goes flat. We have three price constants. P is for product price, Q is input price, and R is the rate of interest. Okay, and this equality holds interconnecting the rate of interest and the discount factor. K0, the initial capital stock, is given. All right. So the firm's problem is this. We need to find an optimal path for the capital stock in this maximization problem, which is profit, simply. So this is total revenue, and we have an expression for the costs. Okay. This part of the expression describes the change in capital from t to t plus 1. So this is the size of capital investment. And this part of the expression describes the capital stock that is transferred from period t to period t plus 1 after depreciation. And on this basis, we have the Bellman equation. The Bellman equation is this. Supposing we have feasible choices, this is the one period return function. So this is the Bellman equation, and this we are supposed to solve this Bellman equation to find the value function and to find the optimum policy function. First, we need to choose the appropriate strategy to solve the Bellman equation. First, before doing anything, we need to find boundedness for the return function, because by itself the production function is not bounded, is unbounded. And here we can take the usual path. So now we can find a state space, a bounded state space. This is the plan. Let's try to find a bounded state space. So something like this. So this is the state space, and we are trying to find a closed interval on which the state moves. In other words, from which the state cannot leave. And if we can find such a closed interval, then the return function can be regarded as bounded. Let's try to do so. So we have this profit function. This is a simple one. This is the simple one period return function. And on a competitive market, profit is 0. And assuming that profit is 0, we have this result. We have this result, of which we can express a nonlinear difference equation in K for next period capital stock. And given that we have no technological change, technological improvement, we have no increase of the population. Actually, the population is excluded from this exercise. There must be a steady state in which, so let's introduce Km as the steady state capital stock. So in the steady state, it's true that this equality holds. This equality holds. And after some steps, we have this equality. Which is easy to put into a figure. This is K. So this is production function with the constant prices as a parameter. And this is the linear function of the amortization, of the depreciation of the capital stock. And what this equality says is this point. So at this point, output and capital depreciation are the same, they are equal, and this is useful because in cases where capital stock is higher than the steady state capital stock, then capital depreciation is higher than output. So we are here, for instance. So capital depreciation is higher than current output, and capital stock must decline. So actually, it is never optimal to choose a capital stock for next period, something like this. It is always irrational, it is always not non-optimal, So we can rule out this option. So we can have a closed interval for the state space in the simple way, and this is going this is going to be an appropriate upper limit for the state space. So this is the state space we have, and this is a closed interval, and on this closed interval the one period return function is bounded, and we have this correspondence. It's always non-empty for any non-zero positive capital stock. So everything is closed and compact. So the return function is bounded, and we can start solving the problem. Okay, so these were the preliminaries. Now we want to solve the Bellman equation. And when solving the Bellman equation, we need the first derivative of the value function. Let me show you. So this is the Bellman equation, and this is the Bellman equation, I mean. And given that our control variable is y, so next period capital stock, to get to the first order condition, we need to derive this Bellman equation with respect to y, and when doing so, we would need this derivation, and we cannot do this because the value function v is the unknown of the Bellman equation, so we cannot do this. To do so, instead, so we can get to the derived function of the value function by using the Benveniste-Sheinkman formula. So we can derive the one period return function under specific conditions. So before, and this is one of my key points in this exercise, before setting down to solving a Bellman equation, a dynamic optimization problem, we need to check very carefully. We need to check if some basic assumptions hold at all. In the previous lecture, we went over all the key assumptions, and in practice, we are supposed to check these assumptions. So let's go one by one. Assumption 4.3, the state space is a convex subset of the L-dimension Euclidean space. Gamma, as the correspondence is non-empty, compact valued, and continuous. And this is true. This is true. Assumption 4.4. A is the curve of gamma k as a set. So A is defined in this way. This is a set consisting of ky points with coordinates a, k, and y, supposing that the y coordinates are feasible choices, where gamma k is described with this closed interval. and one period returns are described by this one period return function. As all the intervals are closed and compact, we can conclude that it is bounded. The one period return function is bounded. As fk, the production function, is continuous, it follows that the one period return function is also continuous, and it is true that beta as the discount factor comes from the open interval 0, 1. So we can conclude that assumption 4.3 and assumption 4.4 hold. So there is V as a fixed point, as the unique fixed point of the Bellman operator. Okay, assumption 4.5, as the one period return function is this, this is the first derivative in the first variable, and it is sure that it is positive, so f is strictly increasing. Great. F is strictly increasing. Holds. Assumption 4.5 holds. Assumption 4.6. Gamma is monotone in the sense that if it is true then it is implied that it is a subset of gamma at the higher value of the state. So assumption 4.6 also applies. According to theorem 4.7, V is strictly increasing. So you can see that what we are doing is going over the assumptions and the theorems in the key chapter and checking whether the necessary assumptions and the important theorems hold or not. Assumption 4.7, F is concave. We have many ways to prove that function is concave, one of which is the Hessian matrix, but trust me, it doesn't work here, so we cannot substantiate that F is strictly concave. So we need another strategy. So let's pick 2 points in the plane and let's have a constant of the open interval 0, 1. According to the usual definition of concavity, F valued at any convex combinations of ky and key prime y prime is higher than any convex combination of f valued at ky and k prime y prime. So let's try to demonstrate that f is concave along this line. So let's have the convex combinations. This is the first convex combination, and this is the second convex combination. And then let's put these points into the one period return function, which equals, I won't do all the steps because we don't have the time to do everything together, and this is simple algebra, so you can easily do it. You can easily do it at home. So after a few steps, we have that it's easier than it may look. And now we use the strict concavity of small f. So this inequality holds given the strict concavity of f okay, which is equal to, this was the last stage from which it follows. And this is very important. So because of the strict concavity of the production function, assumption 4.7 applies, and f, the one period return function, is strictly concave. Okay, so assumption 4.7 holds. Assumption 4.8. Gamma k is convex in the sense that for any appropriate constant, it is true that if y is a feasible choice at k and y prime is a feasible choice at k prime, then it follows that any convex combination of any feasible choices or feasible choices for any convex combinations, any convex combination of the state. So before doing anything, I think we suggest have a look at the graph of gamma. So we are trying to analyze visually the state, the graph of gamma. So we have a maximum value for the state, and the same maximum value applies to the feasible set. So the upper bound for the state is the upper bound for the choice. So this is actually, this is a square. So this is A, the figure, the graph of the feasibility set, and assumption 4.8 practically means that any, let me use different colors. So for any possible states, the convex combination of any feasible choice, two feasible choices, is also an inner point of the graph. So as this is a square, it's obvious, it obviously holds. So we don't need to do anything else about it. This is a rectangular, and a rectangular is a convex shape, so it obviously holds that gamma, the correspondence, is convex. Next one, assumption 4.9, fky is continuously differentiable at any inner point of A, meaning the graph of gamma. It is true. So by definition, f is a differentiable, a continuously differentiable function. So the conditions of theorem 4.11 are met. So we have checked that assumptions 4.3 and 4.4, and so consequently theorems from theorem 4.2 up to theorem 4.5, everything works, and these theorems together ensure that the solution of the functional equation and the solution of the sequential problem exactly coincide. Okay, so just we before going on, at the logarithmic utility function, f, the return function, was unbounded from below, so we needed a special approach to solving the problem. Okay, so this is just a reminder we have covered. So in such cases, we must be careful when there is no lower bound for the return function. So if we have, just to be more specific, if we have a logarithmic utility function, we cannot solve the problem with setting a closed and compact interval for the state and for the correspondence, because at 0 the utility function would tend to, okay, at 0, it doesn't make sense to say that the logarithmic function exists at 0. So as consumption approaches 0, utility would approach to negative infinity. So if we had a logarithmic utility function, we should be more careful. But now we don't have a logarithmic utility function. We don't need to pay attention to these concerns. Okay, so continuously differentiable. So here we go. We have the Bellman equation. And now, after checking the basic assumptions, now we may try to solve directly or in some way the Bellman equation. All right. First order condition. So the choice variable is y, so we need to derive the Bellman equation with respect to y, and this is the first order condition. Is 0, from which it follows that this equality holds. We don't know anything about, for now, we don't know anything about the derived function of the value function, but the conditions for theorem 4.11 hold. So we may try to get to the v prime function indirectly through the Van-Veniste-Sheinkman formula, or let me show you another way to the derived value function. So let's assume that we have the optimum. This is the envelope condition, so we are going to use the envelope condition instead of the Van-Veniste-Sheinkman formula. Each is fine, so trust me, you can take any path. We could choose the Van-Veniste-Sheinkman formula, but for now, let me choose the envelope condition. Sometimes it's simpler. So let's assume we have the optimum policy function g So if the optimum choice for next period capital stock is described by the policy function, this function, then this is the maximized Bellman equation, or the Bellman equation after the maximization. Okay, so according to the envelope condition, if we want to assess the effect of any change to the value, the maximum, the optimum value of any change in K, the capital stock, we need to derive this equation with respect to K, but we can ignore all the indirect effects. So we don't need to pay attention to how the change in the capital stock affects maximum or optimum value through the policy function. So when we derive the value function with respect to K only directly, we will have this result. Please check just a piece of advice. Please check the Sutter-Hammond textbook, math book, handbook I offered you, I recommended you in the very beginning. There is an excellent description of the envelope theorem. Let me summarize the main result of the envelope theorem. In a maximization problem, we treat some things as given, like the initial capital stock or the discount factor. These givens also affect the maximum value the optimizing agent can receive from optimally solving this maximization problem. And we may be interested in scrutinizing how any change in these givens, any change in any of these givens affects the maximum value. In such a case, we need to derive the maximized value function with respect to that particular given. In this case, this given is the capital stock. But when deriving the maximized value function, the optimum value function, we can ignore those effects that goes through the policy function because they are only indirect effects. So trust me and trust mathematics. When we want to know how any change in the capital stock affects the maximum value, the only thing we need to do is to derive the value function with respect to k. And this is what we have. This is what we have. We are one step closer to the derived function of the value function, because now we have the value function, derivative function of the value function at k, but this holds for any k, so it holds for k prime too, which is the same as this function we are looking for. So this is simple as this. So this is the function we were looking for, and from this it applies so one more step. And this is an implicit, so as you can see, this is an implicit expression for the optimum policy, for the optimum choice y, optimum choice for next period capital stock. This is functionally, this is an Euler equation that describes dynamics of the state variable, which is special. It is a special Euler equation because the optimum choice for next period capital stock is independent of k. So in this case, the optimum policy function is a constant for any k. This is a constant. In other words, the optimum choice for next period capital stock at any k is optimal. So this is a constant. So this is optimal at any k, any state. And it means that the optimum path for the capital stock is stable. So no matter at which k we are at currently, we will choose this constant for next period capital stock, and from that point we are going to choose all the time the same optimum capital stock. So capital stock is going to be constant. So at any t, this is the optimum path for the capital stock. So having all this in the bag, how can we write down the policy function and the value function? The policy function is simple because, as we have seen, we have a constant value. So it is true that at any k, any state, one particular value applies as the optimum value for next period capital stock. Okay, but we need to be tricky when it comes to writing the value function, putting the value function in an explicit form. It can be solved brilliantly simply, in a brilliantly simple way. This is not my invention, but I will show you how it can be solved in a very simple way. Let's use the fact that next period capital stock can be adjusted to the desired level very flexibly. So actually, no matter at which capital stock we are at the moment, recently, we find the optimum capital stock. You remember, this is the optimum capital stock, which is we have just described through the envelope condition, and we can adjust the capital stock by next period. And once we achieved the optimum level of the capital stock, it remains there. So it takes one period for us to get to the optimum level of capital stock, and once it is achieved, we stay there. So by using this fact, it is easy to realize that the value function can be simplified. Okay, so here we are, from which you can realize that the same value function evaluated at the same optimum capital stock next period shows up on both sides. So we can rearrange the value function in this form. From which it follows. I think it's brilliant. Unfortunately, this is not my invention, but it is true that we can use the fact that the capital stock can be adjusted very flexibly, and once we are at the optimum level of the capital stock, we remain there. So it follows that the value function of the problem is this. So here we are. Yes. Okay, we can further simplify this part, but it remains the same, so it's about beauty at this point, but it changes nothing. So let's go on. So we have the policy function and we have the value function of the basic model, in which, and this is the line along which we are going to proceed. In this version of the model, we can adjust the capital stock very flexibly. So we calculate the optimum capital stock, and we can set the capital stock to the desired level next period. And this is not too realistic because capital stock adjustment takes time. So even if we want to, it doesn't matter if we want to adjust the capital stock upwards or downwards. If we want to go upwards, we need to make investment, which takes time. If we want to go downwards, we must rely on depreciation, and it also takes time to achieve the desired. It may also take time, even years, to get multiple periods to get to the desired capital stock. So in a more realistic version of this model, we want to introduce a new way of formalizing the feasibility set, in which next period capital stock is squeezed into a closed interval given by continuous functions. So we have a new correspondence, and in this case we need to recheck if our assumptions hold. So we need to go over the assumptions one by one to check if they hold. We will do it quickly, I promise. Assumption 4.3 still holds because the state space is convex. It didn't change that the state space is given by a closed interval. So the state space is convex, gamma is non-empty, compact valued, and continuous. So assumption 4.3 holds. Assumption 4.4 hasn't changed. Assumption 4.7 hasn't changed. So the next assumption to check is assumption 4.8, the convexity of gamma. Gamma must be convex, and we need to check it very carefully. Let me draw you a figure, a very simple figure of the new gamma we have. So this is the capital stock. This is gamma, and we have two continuous functions to describe the feasibility set. This is the maximum level of the capital stock, and let's pick two arbitrary values for the capital stock. These are the correspondences at these levels, and these are the inner points arbitrarily chosen at k and k prime. At first sight, A, which is the figure, the graph of gamma, it is a convex. It is a convex shape, so it is a rectangular, and rectangulars are convex shapes. So it is obvious that it is convex, but in mathematics sometimes we need to demonstrate the obvious. So let's try to show precisely that gamma, the correspondence, is convex. What we need to show is this. What I'm writing now is not new. It comes from the convexity of gamma, the definition of convexity of gamma according to our textbook. So we need to show that this is true. So any convex combination of these points or is inner point at any convex combination of the capital stocks. Okay, no matter what convex combination of the capital stocks we pick, we have inner point along the line between y and y prime. But let's try to demonstrate that A, the graph of gamma, is convex. The solutions manual offer you a way, but I have found another way, and let me show you my way of demonstration, So if y is an inner point, then it is true. And if we multiply this system of inequalities by an appropriate parameter, we will have this system of inequalities. And at this point, let's put these inequalities aside for a second. And if y prime is a feasible choice at k prime, then it follows what I'm doing now is no more than putting formally that y prime is a feasible choice at k prime. Let's multiply this equation, system of inequalities, not equation, system of inequalities with another constant parameter, and we are going to have this form. Yeah, I think it's correct. And by combining this expression and the previous highlighted expression, we have this expression. It's going to look very complicated, but you will see in a split second that it's very simple and straightforward and convincing. there is only one step remained. Because with okay, let me show you the next step, which is the key. So we need to rearrange this expression. Hopefully I am doing okay. Yeah, I think it's correct. So we are rearranging the previous expression, and I think now you realize what is going on here. Because with some simplification, it follows. And this was what we wanted to demonstrate. So gamma is convex. Gamma is convex. According to assumption 4.5, the one period return function is supposed to be strictly increasing in k, and it is. According to assumption 4.6, gamma is supposed to be monotone in a special sense, but it doesn't hold anymore. So on this basis, by theorem 4.7, we cannot conclude that v, the value function, is strictly increasing. So we need to find another way to show that v is strictly increasing. I think it's important to emphasize that by the fact that gamma is not monotone, it doesn't follow that v is not strictly increasing. It means only that we cannot conclude on the basis of assumption 4.6 that v is strictly increasing. So v can be strictly increasing, but we need to find another way to show it. Okay, so let me show a way of demonstration which is different from the one you can find in the solutions manual. So you can choose either way. Trust me, v is the value function is strictly increasing. Okay, let's try to put the firm's problem into the sequential form. So we are going to use the sequential form, and let's assume that we have the sequence, the optimum sequence of the capital stock by which the firm attains the supremum in the sequential problem. So we have the optimum path for the capital stock. Now, given the initial capital stock, we have the first few stages in the sequential problem. So these are the elements of the presumably optimum path for the capital stock. I will put only a few stages in the sequential problem. We don't need too much. And if we have another initial capital stock which is higher than K0, and by using the fact that F is strictly increasing, we can say that this inequality holds And actually, we don't need to recalculate the previous optimum path, not because it remains optimal. It's highly unlikely that it remains optimal. We don't need the optimum path because we have already had what we need. Because what we really need is this strict inequality, and that we can find another optimum path. So, but given the fact that gamma is non-empty, if this equality holds, then by the fact that f, the production function, is strictly increasing, we can conclude that the value function is also strictly increasing. Okay, so you can find another way of demonstration in the solutions manual, but at this point we are done. So we have gone over all the assumptions. So now we can turn to the problem itself. So we need to maximize the firm's profits for the infinite future given by or described by the one period return function Okay, so this is the objective function. Supposing that we have boundaries for the control variable, which is next period, capital stock. Okay, for ease, let me say that we have a lower bound and we have an upper bound. Okay, for we have two boundaries in the form of inequalities. The Bellman equation can be put in the usual Kuhn-Tucker form. Just as a kind reminder, in nonlinear programming, the Kuhn-Tucker in the Kuhn-Tucker approach, you will have as many Lagrangian multipliers, as many constraints you have. So instead of paying lip service to the problem, let me show you what we do in this Kuhn-Tucker version of the problem. Once again, we are using the Kuhn-Tucker theory just because we have constraints given in the form of inequalities, and this is where the Kuhn-Tucker approach comes into play. So this is one Lagrangian multiplier for the lower threshold, for the lower boundary, and another multiplier, Lagrangian multiplier, for the upper threshold, upper boundary. Okay. From this point, the problem can be solved in the same way. So we need some first order conditions, and it is quite sure that in some cases we will have interior solutions, So the optimum capital stock for the next period is going to be between the boundaries, and in such a case none of the boundaries are active. So in such a case the optimum solution can be found by the first order conditions only, first order condition only. And in some cases one of the boundaries is going to be active, and we want to find some formal expressions to describe, in any of the cases, we want to describe the policy function. So let's start with the simplest case, interior solution. Interior solution, none of the boundaries is active. So in this case, the two Lagrangian multipliers are zero, inactivating both of the boundaries, and we need to solve only this part of the Bellman equation. And here we go. This is what we have. Just like previously, we can describe the optimum capital stock for the next period from the first order condition, which is described, which can be found through the envelope condition or the Benveniste-Sheinkman formula, to your liking. So you can use any of them. So this is an interior solution. Okay. Next case, we are on the lower boundary. We are on the lower boundary. What does it mean? Let's use the same first order condition, because we know that this is an interior solution, but we are on the lower boundary, which means that y is given by this equation. So we can rewrite the first order condition using the lower boundary. It may be surprising, but there is nothing new to this equation. We know that this equation gives an interior solution. So if the capital stock is higher than k lambda, then next period capital stock is given by the lower bound. If k is not higher than the threshold, then we have an interior solution, so we have nothing to do with the boundary. In the third case, we are on the upper bound. We are on the upper bound, and it was not boundary, just bound. To err is human. So we are on the upper bound, and we will do the same. So we know that by using the equation of the upper bound, this equation leads to an interior solution. So if the capital stock is lower than the threshold level, then it means that the firm is constrained in increasing its capital stock. And now we have a complete description. On this basis, we have a complete description of the policy function, because we have discovered all the three cases. So we are on the lower bound if k is higher than the threshold level. We are on the upper bound if k, the capital stock, is lower than the threshold level. And we have an interior solution if we are between the thresholds. Okay, and the optimum, so the interior solution is described. This is just a reminder because we have already covered this. So the optimum solution is described by this implicit expression. Okay, so we have a complete description of the policy function under the assumption of boundaries with respect to the feasible choices. In point B of the same exercise, we have a different setting. Instead of having a constant investment cost, now we have a convex function according to which quick capital adjustment is penalized. And now, under this setting, the firm's problem looks this way. So once again, instead of a constant investment or capital cost, now we have a convex, strictly convex cost function. This is the function C, and the argument of the investment function, investment cost function, is investment. And the higher the investment, the higher the cost. So once again, quick capital adjustment is penalized. The Bellman equation is the following. It looks really similar. We have next period capital stock as the choice or control variable. So this is the Bellman equation, and at this point we should check all the basic assumptions, which we won't do now to save time. Trust me, everything is fine. So all the basic assumptions hold. So we can proceed to solving the Bellman equation. the decision variable is y, next period capital stock, so we will do the same. We derivate the function, the Bellman equation, with respect to y to get to the first order condition, which is equal to 0, and on this basis C prime equals to V prime. Okay, and the task here is to say something intelligent about the policy function, which is responsible for setting next period capital stock to the optimum level. So practically, the optimum choice is summarized in a policy function and in this task we need to figure out some basic characteristics of this policy function. We are interested in two things especially, whether it is increasing or decreasing in k in the state, and the slope of the policy function. So we have a figure. We're gonna use this figure extensively in these exercises, so it's gonna be useful. What I'm doing now is drawing a figure on the basis of the first order condition. This is the right hand side of the first order condition, and this is the left hand side. And you can see that given that one of the functions is increasing, the other is decreasing, there is a unique, I can do it better, there is a unique optimum choice. So what we want to know if it is increasing or decreasing in k first. So it's easy to realize that k comes into play through C prime, and if we increase k to k prime, then it shifts the curve to the right with the point of intersection. So we can say that the policy function is increasing in k. So this is the intuition, this is the intuitive answer that g, the policy function, is an increasing function of k. Okay, we need a formal demonstration. So to demonstrate that policy function g is increasing in k, we will assume that g is decreasing. So we are assuming the exact opposite. Instead of g being increasing, we assume that g is strictly decreasing. So if k prime is higher, assume if k prime is higher than k, then gk prime is lower than gk. So we are assuming that the policy function is strictly decreasing in k. Let's use the first order condition. Initially, with k, we have this equality, which we can rewrite by using the policy function, actually the same at different k's. Okay, and given that v, the value function, is strictly concave, this inequality holds. Okay, from which it follows, by highlighting the relevant parts of this inequality, it follows that another inequality holds, from which, by the strict convexity of C, it is strictly convex. It follows that this inequality holds, and after rearranging this inequality, we get to this result. And first, let's have a look at the right-hand side. This is positive. This is positive because delta is between 0 and 1, and k prime is higher than k. So the right-hand side is positive. So the left-hand side is also positive, which is possible only if j k prime is higher than gk. So g must be increasing. Okay, so this is one thing we know for sure. The other thing, okay, so gk is increasing in k. The other thing we want to know is the slope of the function, policy function. So it's very simple, I promise. So let's assume that we I've made a mistake. This is k prime. So let's assume that we replace k with k prime, and k is higher, k prime is higher than k. So what happens in the policy function when changing from this value to this value, it is as if I added this term to the argument of C prime, because initially we have this value, and if I add this expression to the argument, we will have this expression, and you can realize that some parts fall out. So finally we replaced k with k prime. So when replacing k with k prime, actually we add this term to the argument of k or of C prime. So the whole function, I need a different color. So the whole function moves to the right with to the extent of this expression. So this is the distance along which C prime, function C prime, moves to the right. At the same time, y along the horizontal axis also moves to the right, but the distance of the movement is lower than the movement of the function C prime. So what we know for sure is an inequality. This is the movement of the optimum choice along the horizontal axis, which is smaller than the movement of function C prime. And as a consequence, with some simple rearrangement, we receive this result. This is simple algebra. And given the fact that k and k prime were both arbitrary, so they can be close to each other, then we can say that the slope of the policy function is less than 1 for sure. So now you can say that with some really simple analytical tools, we can characterize the policy function quite strictly.